Hey everybody, welcome to the first of two videos that you're watching because I am at the hospital with my wife from delivering our second baby. So in this video I will just set up the topic for the rest of the course. We will spend the rest of the course talking about partial differential equations. So this video is an introduction to those equations. We will solve a few of them, but they will be pretty basic examples. And then in the next video we will move on to studying our first sort of big class of partial differential equations. So for this particular video, here is what we want to do. I want to define PDEs for you, and from henceforth I will stop saying partial differential equation. It's too much to say. I will say PDE. We'll briefly talk about why you want to study them, and then I'll give you some basic examples. So by the end of this video, you will understand what a PDE is, and you will be able to solve a few carefully chosen examples. What is a PDE? Without getting too formal about it, a PDE is an equation involving partial derivatives, as the name would suggest. So we've already seen such a thing. This is the equation that defined harmonic functions for us in the complex analysis section. So what is this saying? This is saying, find me a function whose second partial with respect to x plus the second partial with respect to y is 0. So it's important to note that solutions of PDEs are functions. So a solution of this PDE is, again, any function whose second derivative with respect to x plus the second derivative with respect to y is 0. So here is such a function. If you partial this guy with respect to x twice and you partial him with respect to y twice, you get 0 for both things. So this is sort of a cheap way to generate a function who is a solution of this equation. Notice on the other hand, though, this guy is not a solution. His partial with respect to x after two iterations is 0, but the partial with respect to y after two iterations is 6y. And so back up here you would have written 0 plus 6y, and that is not equal to 0. So these equations work just like normal algebraic equations. You have a notion of a solution. A solution is anything you can substitute back into the original equation and see if you get a true statement or not. This guy, if you substitute him in here for you get something true. This guy, if you substitute him in for you get something false. Okay, so the idea of the equation is just like any other equation, except our solutions now are functions. Our solutions aren't numbers or whatever else. We use the term PDE to distinguish the kinds of equations we will study from what are called ODEs. An ODE is a differential equation in which all variables depend on only one other variable. So ODEs don't have partial derivatives because if y only depends on x, for example, you don't need to talk about a partial derivative. You're just talking about the normal derivative dy dx, just like in Calc 1. So an ODE is just single variable calculus, essentially. So the differential equations course that many of you have taken already is an ODE course. All of our variables depended on a single independent variable, and it was usually time in physical context. So anyway, some of you have taken an ODE course, so we use PDE to distinguish from that. And I guess I should mention here, the material we will do for PDEs, I do not assume you have had ODEs. I don't assume you've had the ODE course because not all of you have had that course. So I'm certainly not going to assume that you just know how to solve, an nth order linear homogeneous differential equation or something, things that you would learn in a differential equations course. So we will need some ODE theory to help solve PDEs, but I will introduce that theory to you as we need it. I won't assume that you know it. Okay, so why study PDEs? Why study anything? They are nice. They are, to some people, aesthetically pleasing. They are not my flavor of mathematics because the theory gets messy pretty quickly. I find the theory not particularly aesthetically pleasing, but I do find them interesting. So the reason that most people study these things are, it's mostly mathematical physicists and people like this that actually study PDEs. You study them because they model physical phenomena. So suppose you want to model the movement of vibrating strings, for example. This is one of the first examples of PDEs you will see. So I guess you have to be precise about that. You want to know the displacement of the string from equilibrium. So just to give you a visual here, this string right now is in equilibrium. If you pluck this, then it will move, right? So if you want to know where this particular black dot is, so let's just watch it move, right? So this particular black dot is like now so now this black dot is at, say, -2 or something. You measure downward displacement as negative, but as it goes up, now it's at displacement, 0.5 or something. So anyway, if you want to measure that black dot's distance from equilibrium, well, this is a movie, so the black dot's displacement depends on time, doesn't it? Right? So as time flows, this displacement changes. But if you think about this black line is sitting on the x-axis, so this maybe stretches from 0 to 5 or something, right? This particular black dot, his position depends not only on time, but of course where he is above the x-axis. So if this tick mark here is like a 1/2 on the x-axis, the displacement of this black dot depends on that position on the x-axis, that 1/2, and it also depends on time. So as you watch a movie like this flow, if you want to describe the placement of any of these black dots inside this string, you have to know what time it is. You of course also have to know, where above the x-axis the dot is. So all of that to say, that's why I say here, let uxt be the string's displacement. So the displacement depends on the time and also where you are relative to the x-axis. So the displacement function is a function of two variables. If it were a function of one variable, then we would be back in ODE land, we would be in single variable land, but this is a function that depends on two things. Therefore, it is natural to assume that partial derivatives will show up if you start taking derivatives of this guy. Okay, so it turns out that if you let rho be the density of the string and t be the tension of the string, both assumed to be constant for now, you can show that this is true. And I'm not going to show it to you now, but you can show that the second partial with respect to time of the displacement equals some constant c squared, which is defined down here for you, times the second partial with respect to x of the displacement. So this partial differential equation here, called the wave equation, will model the movement of that plucked guitar string. Okay, so if you want to know the actual displacement function, you want to actually know where things are on the string, you first need to solve this equation. If you solve this equation, and you'll have to know some additional data like where the string starts, does it start at equilibrium, does it start already raised off equilibrium, or whatever. But once you know some sort of initial data, and you want to then know the displacement of the string, you would have to solve this PDE to get that string displacement. So U itself, right? Where are we going? The function U itself actually is what the string is, right? It's actually giving you the movement of the string. So if you want to know where these black dots are at a particular time relative to the x-axis, you got to solve this equation. Okay, so why do you study PDEs? I mean, people study all sorts of things because they like them, but usually people study these things because they model things like wave phenomena, they model heat flow, they model all sorts of things, fluid flow. So we'll be able to see some of these applications, but we only have 4 weeks or so left of class, so we can't get too deep into it. Okay, now let's just move on to solving some examples here is our first PDE. It says, find me all functions whose second partial with respect to x is 0. Okay, so again, find all functions u so that the second partial is 0 with respect to x. So I'll let you think about this for a second, but the analysis goes kind of like what we've done already. You just do what's called partial integration. So what does uxx equals 0 mean? Well, that would have to mean that ux itself just has y stuff in it, right? Because if ux had x stuff in it, then the second partial would not be 0. So in other words, you integrate this guy with respect to x, and what do? You get a constant, but you get a constant with respect to y. Okay, but if ux equals y stuff, that implies that u itself, if you integrate again with respect to x, is that y stuff times x plus some other free-floating y stuff. And there you go. Any function that looks like this is a solution of this equation. And of course, you can check that this works by just starting with this function here and taking its second partial with respect to x and seeing that you do get 0. So if you partial this guy with respect to x once, what happens? G of y disappears, and all you're left with is an f of y. And then if you partial y stuff with respect to x again, you get 0. So linear functions like this, linear over x, those functions satisfy this equation. Those are the solutions of that equation. So just as an example here, note that y squared x plus sine y is a solution. It has this form. If you partial this guy with respect to x, what do you get? Get a y squared. Partial that again with respect to x, it disappears. But something like this, which does not fit this guy's form, is not a solution. So if you partial this guy with respect to x, you get 2xy squared, right? And then you partial that with respect to x, you get 2y squared, which is not 0. So here's something for you to try on your own. Solve uxy equals 0. So go ahead and, if you'd like, pause the video and try this, and then I will show you the solution of this. So assuming you've just paused the video and have a potential solution, let's just walk through what happens. You integrate with respect to y to peel off that second partial with respect to y, and you learn that ux is anything with x's in it, but no y's. Right, so ux is just x stuff. Then you partially integrate with respect to x, and you get something that looks like this. Capital F of x, where capital F prime equals little f, and when you partially integrate with respect to x, you pick up a plus constant, but constant with respect to x. So you can have any free-floating y stuff you want. So the solution of this is any function where the x's and y's are separated by a sum. Right? That's what this is saying. Any function that looks like this is a solution. So notice this guy here is a solution. If you partial him with respect to x, you're just left with what? Yeah, so partial him with respect to x, you get 2x, right? And then partial that with respect to y, you get 0. But notice something like this is not a solution. If you partial that guy with respect to x, you get y e to the xy, and then you partial that with respect to y, you do not get 0. Okay, so our first tool for solving PDEs is this partial integration trick. So just sort of peel off the derivatives one by one, and as you go, you pick up constants with respect to the given variable, which means you get some free-floating function in terms of the other variable, just like this. Okay, so now let's move on to something more complicated. The previous two examples involved just a second-order guy equaling 0. So let's move on to something that involves not only a second-order guy, but the function itself. So let's say in English what this wants. This wants you to find all functions whose second partial with respect to x equals the negative of the original function. Okay, this PDE says that uxx equals negative u. So you're trying to find all functions whose second partial with respect to x equals the negative of the original function. So to sort of wrap our minds around how we would do this, let's just suppose for a second that u were just a function of x. Because just like back here, in these examples, you're trying to find functions of two variables. So your solutions can have both x's and y's in them. But let's just start by thinking about what functions that are just a function of x could solve that equation. Well, if u is just a function of x, then the second partial with respect to x is just the normal second derivative. And so what we're trying to solve is u double prime equals negative u. And now if you've taken the differential equations course here, this is the kind of equation you would have solved in about the third week of class. This is a second order linear DE. It's just u double prime plus u is 0. Okay, but of course not all of you have had that course, so let's just think about, in English, what this is saying. You need to find a function whose second derivative is basically the original function, right? So u double prime is basically u, except you've picked up a negative sign. So can you think of some sort of familiar function from Calc 1, Calc 2, whatever, whose second derivative is the negative of itself? If you think about it long enough, so what functions have the property, what single variable functions have the property that their second derivative is basically just themselves, but negative? If you think about it, you will get a couple of answers. You will remember that, oh, sine works, right? Because u prime, if u is sine, is cosine, and then cosine prime is negative sine, right? And the same thing works for cosine. So if you prime cosine, you get negative sine, and then prime of negative sine is negative cosine. So sine and cosine have this property that if you prime them twice, you get basically the same function back, but you pick up a negative sign. So you would see this in a differential equations course. The solution set of this equation is just this. You can take any constants times sine and cosine and then add the result together. So for example, 5 sine is a solution of this. 7 cosine is a solution of this. 5 sine plus 7 cosine is a solution of this. So in general, ODEs, these differential equations you would see in the course here, they have this nice property that once you find a solution or two, you can scale these solutions by constants, and you still have a solution. And you can add solutions together, and you will still have a solution. So you can just check, of course. Like you can just take this, plug it in here, and see you get the things negative. So if you take this guy and double prime it, what do you get? You get a negative c1 sine x minus a c2 cos x, which is what you're supposed to get. Okay, so of course, in this setup here, we can't just assume u is a function of x, right? Because u could also be a function of y. U in general will depend on both x and y. But what this is really saying is like, look, can we just take this logic here and extend it to this? This is saying kind of the same thing. My second partial with respect to x is supposed to equal negative of myself. The way you can get that is, well, suppose these c1s and c2s aren't literal constants. Suppose that they were functions of y. So suppose the c1 is like a y squared. The c2 is like an e to the y. The same logic will work. So here, if we replace those constants with functions of y, we get a solution of the PDE. So now, again, you can check. Put a y squared there. Put a y cubed there. Whatever. Those are irrelevant because this PDE here only involves partials with respect to x. So you can check here. If you plug this into here, you will get something true. So what happens here? The partial with respect to x, I get a c1 of y cos x minus c2 of y sin x. And if I prime that again, I get a negative c1 of y sin x minus c2 of y cos x. Okay, so here's the solution of this. So in this case, there's no technique really. We just kind of thought about it. We first thought about what this would mean for a single variable function, and then we ratcheted that up to now including functions of y. Okay, so we've now reached the end of our first video. What I wanted to point out though is that a PDE has arbitrary functions in its solution in general. So if you've seen ODEs before, which again not all of you have, but if you have, you should remember that in a differential equations course, ODEs generally have arbitrary constants in their solution. But now when we have more than one variable, those constants become constants with respect to other variables, if you like. So now you have free-floating functions of y that are arbitrary in this guy's solution. Back here, you have free-floating functions of both x and y, just arbitrary functions, right? Back here, where was it? Oh, okay, so I already went too far, yeah. So right here. This involved arbitrary functions of y, the solutions of this equation, this uxx equals 0. So in general, you would expect to see arbitrary functions in a solution of a PDE. Okay, so at the end of this video, you can now solve basic things like, this is about as complicated as we got, uxx plus u equals 0. So you could try your hand at uyy plus u equals 0. You could solve something similar to this. Or you can solve little ones like this that just involve unpeeling a partial integral a couple of times. So in general, most PDEs, of course, are way more complicated than what we just did here. So in the next video, we will turn our attention to a particular class of PDE that we can solve using some geometry. So that's it for now.